projecting something at negative 9.8 meters per second squared, we call that free fall. Free fall is falling in the absence of all other forces but gravity. No air resistance, no parachutes, no strings, no bungee line. When things are falling, they're accelerating. Because they're accelerating, we will use only equations that have acceleration in them. So one of our initial equations of the change in velocity over time, and commonly we will have to find the final velocity. So it's good to recognize it in this form as well. We're not always going to be given the time. So another equation we have from our formula chart is the final velocity squared, initial velocity squared, divided by 2 times the distance. Again, a lot of times we have to find the final velocity. So a little bit of algebra. I'm going to cross multiply. A equals 2 times b. Bring down my other terms. Inverse. Inverse of subtracting initial velocity is to add it to both sides. Don't forget to carry your square. Bring down my last term. And the last step that I could do would be to take the square root of both sides to cancel out that squared. The final equation we have that has acceleration from our formula chart is to solve for the displacement of something. So we look at the initial velocity times time plus 1/2 at squared. Very commonly, the initial velocity on all of these is oftentimes 0, especially and always if we're talking about something being at the top. If we start at the top and fall down, the initial velocity is 0. Acceleration is still negative 9.8, but at the top the initial velocity is 0. So we can simplify this one to 1/2 at n squared, because 0 times anything is 0. The other common way to rearrange this one would be the time that it takes something to fall would come from, and I won't show the algebra on this one. I'm showing dy here because remember that we're falling, and we're using gravity to do that. So these are kind of my common equations, and you should recognize them in the different forms. If things are falling, but not only due to gravity, then they're not necessarily in free fall. When we have multiple directions of motion, we have what we call a projectile. We're having 2 dimensions of motion. So here I could be rising while moving forward, rising while moving forward. And I'm going to slow down while still moving forward. Eventually I get to the top where I'm no longer rising, so my vertical velocity is 0, but I still have horizontal velocity. And then as I start to fall, I'm going to speed up in my vertical direction, but still maintain that forward velocity. This is what we call a projectile. Projectiles follow the path of a parabola. So rules that we have are vertical velocity. We are accelerating because of gravity, so we will use those 3 equations we started with, our 3 acceleration equations. Horizontally, we don't have any gravity, so we have constant motion. The only equation that we have that shows constant motion is our very initial one. So we'll represent it with some x's here. No acceleration because it's constant. A few other nice rules to remember about parabolas. On a parabola, if this was graph paper, then the value that I have here would be the same as the value that I have here. But one would be positive, one would be negative. So I could move up at a speed of 10 meters per second. And over here, same spot, I'd be moving down at negative 10 meters per second. I I could still be moving forward at the same time. And that could be any value, 2 meters per second, but because it's constant, it would still be 2 meters per second over here. To figure out if something is moving down and forward at the same time, their relative velocity, or what you actually feel, we're again looking at kind of that Pythagorean theorem method. So I'm moving forward and down, I've got my triangle shape. So I take my x velocity and my y velocity and plug it into my Pythagorean theorem to find the result, or the relative velocity. So my resultant velocity would be my a squared and my b squared to solve for my c squared.